Hello students, we are now going to discuss the sets of numbers. The entire numbers are included into four sets, apart from the imaginary ones. The first set of number is n set, which includes 1, 2, 3, 4, 5 to plus infinity. Why do we call it n set? Do you know? It's very interesting because the elements of n set are present in nature. We can count 1 tree, 2 trees, 3 trees, 4 trees, etc. 1 animal, 2 animals, 3 animals, and 4 animals. 1 man, 2 men, 3 men, and 4 men, etc. And such elements are seen in nature. We can count it. So it's called the n set. The next is the z set. Why do you call it z set? Z set includes n plus all negative integers including 0. Why do we call it z set? You know that z is the ultimate letter of the English alphabet. And the z set is the ultimate set of numbers. It includes n set, or positive integers, all negative integers including 0. So it's called z set. And next, q set. Q set comprises all positive integers. That means q set is equal to z set plus all positive and negative fractions. Such as you see, z set is equal to all, q set is equal to all positive and negative integers, all positive and negative fractions including 0. So z set is equal to, q set is equal to z set plus all positive and negative integers. Why do you call it q set? You know that every fraction, immaterial whether negative or positive, is the fractional form of a quotient. Do you know it? All fractions, positive and negative, are the fractional form of a quotient. So this set is denoted as q set. Do you remember it? Q set is equal to z set plus all positive and negative fractions. Why do we call it the q set? You know that every fraction, immaterial whether positive or negative, is the fractional form of a quotient. So it's denoted by q set. The next and the last is the r set. And it's surely, evidently indicates the numbers, real numbers. And r set is equal to q set plus all the irrational numbers, such as root 2, root 3, root 5, root 6, etc. You see? I am directing you. N set is equal to 1, 2, 3, 4, plus infinity. All positive integers n set comprises. Then z set is equal to n set plus all negative integers including 0 is equal to minus infinite, minus 3, minus 2, minus 1, 0, 1, 2, 3, plus infinity. This is called Z set. Next comes Q set. I told you, why do you call it Z set? Because Z is the ultimate letter in English alphabet. Likewise, the Z set comprises all the integers including 0 immaterial, whether positive or negative. Q set is equal to Z set plus or positive and negative fractions. Why do we call it Q set? Because every fraction is the fractional form of a quotient. The quotient is also a fraction, so it's called the Q set. Then the last but not the least is the R set, which is equal to Q set plus all irrational numbers. R set is equal to Q set plus all irrational numbers, such as root 2, root 3, root 5, etc. But in the last class, I told you, Greek mathematician, who is called the founding father of geometry. Euclid is called the founding father of geometry. And now Euclid's lemma, Euclid's division lemma. How to divide a dividend by the divisor. And how to express a division in terms of the dividend, the quotient, and the remainder. You see, I am citing an example. We have a basket of mangoes. We have a basket of mangoes. If we put them in twos, one mango remains surplus. If we put them in threes, two remain in surplus. If we put them in fours, three remain in surplus. If we put them in fives, four remain in surplus. If we put them in sixes, five remain in surplus. But if we put them in sevens, no surplus remains. What is the number of the mangoes? How can you tell me? What is the number of mangoes? We have a basket of mangoes. If we put them in twos, one surplus remains. If we put them in threes, two surplus remain. If we put them in fours, three surplus remain. If we put them in fives, four surplus remains. If we put them in sixes, five surplus remain. But if we put them in sevens, no surplus remains. How to answer the question? What's the total number of mangoes in the basket? How to know it? We put them in twos, threes, fours, fives, and sixes. Leaving surplus, we'll have to find out the LCM of these numbers. 1, 3, 2, 5, 3. Three, 1, 1, 2, 5, 1. So the LCM is implies the LCM is 2 into 3, 6 into 2, 12 into 5, 60. LCM is equal to 2 into 3 into 2 into 5 is equal to 60. This is the LCM of the number of mangoes that leave surplus. Because when you put them in sevens, there is no surplus. Let's see whether we'll subtract 1 from 60. 59. We'll have to verify whether 59 is divisible by 7. You see, if we subtract 1 from 60, then what happens? And divided it by 2, 3, 4, 5, and 6. The surplus must be 2, 3, 4, 5, etc. But let's see whether it's divisible by 7. If it's divisible by 7, and 59 must be the answer. Do you follow my point? If we subtract 1 from the LCM of certain numbers, and 2, 3, 4, 5, 6, the remainders must be respectively what? 1, 7, 2, 1, 2, 3, 4, 5, 6 is equal to, divide 59 by 2, 1 must remain, by 3, 2 must remain, by 4, 3 must remain, by 5, 4 must remain, by 6, 5 must remain. But we are sorry that it's not divisible by 7. We are sorry. What to do? You see, if we subtract 1 from the LCM of 2, 3, 4, 5, 6, and divide 60 in 59 by 2, 3, 4, 5, 6, etc. The remainder must be 1, 2, 3, 4, 5. It's evident, trivial. But let's see whether it's divisible by 7. No, it's not divisible by 7 because it leaves the quotient 8 and the remainder 3. Let's see. 60 into 2, 120. And you see that 120 must be divisible by 2, 3, 4, 5, 6. 120 must be divisible by 2, 3, 4, 5, 6. And if we subtract 1 from 120 and divide 119 by 2, 3, 4, 5, 6, the remainders must be 1, 2, 3, 4, 5, etc. You see? And let's see whether it's divisible by 7. Yes, it's divisible by 7. And the answer is 120. The basket comprises 120 numbers of mangoes. Do you follow my point? And if we divide 119 by 2, 3, 4, 5, 6, the remainders must be 1, 2, 3, 4, 5 respectively. And if we divide it by 7, there will be no surplus, there will be no remainder.